Download this code from codegive.com, link in the description below. OK, let's dive into the tree vertex splitting problem, focusing on a greedy approach, with some discussion about why greedy might not always be optimal, and with a Python code example. I'll frame this as if I were explaining it during a lecture/tutorial. The tree vertex splitting problem, an in-depth look. Introduction. Imagine you have a tree, a connected graph with no cycles. Each node, or vertex, in this tree has a value assigned to it. These values could be positive, negative, or zero. Our goal is to transform this tree into a new tree such that the sum of node values in each connected component of the new tree is non-negative. We achieve this transformation by splitting nodes. What does splitting a node mean? When we split a node, we essentially create copies of that node, each with a portion of the original node's value. We then distribute the edges incident to the original node among these new copies. The objective is to split nodes in such a way that 1 value redistribution * the total value of all copies of a split node equals the original node's value. 2 component non-negativity * after splitting, the sum of values in each connected component of the new tree must be greater than or equal to 0. 3 minimizing splits, ideally although not always guaranteed in the greedy approach, the goal is to keep the number of splits as low as possible. Formal definition. Input a tree T equals V, E, where V is the set of vertices, nodes, and E is the set of edges. Each vertex V set membership symbol V has a value val, V, associated with it. Output a modified tree T, created by splitting vertices in T, such that the sum of values in each connected component of T is non-negative, and, ideally, the number of splits is minimized. Why is this problem important? The tree vertex splitting problem is a simplified model for various resource allocation and distribution problems. Think of network load balancing * nodes represent servers, and values represent the load they're handling. Splitting could represent distributing the load to new servers to prevent overload. Financial modeling * nodes represent assets, and values represent their profitability. Splitting could represent restructuring assets to ensure each division is profitable. Data partitioning * nodes represent data stores, and values represent their relevance to a specific query. Splitting could represent creating smaller, more relevant data partitions. A greedy approach. A greedy approach attempts to make the best local decision at each step, hoping that this leads to a globally optimal, or near optimal, solution. Here's a common greedy strategy for tree vertex splitting. 1. Root the tree * choose an arbitrary node as the root of the tree. This allows us to process the tree in a top-down, or bottom-up, fashion. 2. Post-order traversal. Bottom-up. A key idea is to perform a post-order traversal of the tree. This means we process the children of a node before we process the node itself. This is crucial because we want to ensure that the subtrees rooted at the children are already fixed, i.e., their components have non-negative sums, before we deal with the parent. 3. Value aggregation * during the traversal, for each node V. Calculate the sum of values in the subtree rooted at V. This is done by summing the values of V itself and the subtree sums of all its children. Let subtree _sum be the subtree sum. If subtree _sum is negative, we need to do splitting. We split at the current node. This ensures that at least the current subtree has a non-negative sum. 4. Splitting decision. If subtree _sum 0, split the current node. Split value equals subtree _sum. We remove this from current node and pass to the child. Split count plus equals 1. 5. Continue asterisk repeat steps 3 and 4 until the root node is processed. Caveats and limitations of the greedy approach. Asterisk not always optimal asterisk the greedy approach is not guaranteed to produce the minimum number of splits. It's possible that a different splitting strategy, considering a wider scope, could result in fewer splits. Asterisk order dependency asterisk the choice of the root node can sometimes affect the outcome, although not always significantly. Asterisk potential for unnecessary splits asterisk the greedy approach might split a node even if there's another way to rearrange the values in the subtree without splitting, but that would require a more complex, non-greedy algorithm. Python code example. Explanation of the code. One node class asterisk a simple class to represent a node in the tree. It has a value attribute, the node's value, and a children attribute, a list of its child nodes. 2 tree underscore vertex underscore splitting underscore greedy, root, function asterisk. Asterisk takes the root node of the tree as input. Asterisk initializes split underscore count to 0. Asterisk defines a recursive helper function post order, node. Asterisk non-local split underscore count asterisk this is important. It tells the post order function that split underscore count is a variable defined in the enclosing scope, i.e., the tree underscore vertex underscore splitting underscore greedy function. Without this, the split underscore count inside post order would be treated as a local variable, and changes to it wouldn't be reflected in the main function. Asterisk calculates the subtree underscore sum by recursively calling post order on each child and adding the results to the node's own value. Asterisk splitting decision asterisk. Asterisk if subtree underscore sum is negative, it means the subtree needs to be fixed. Asterisk increments split underscore count. Asterisk we remove this amount from the current node value. Asterisk returns the subtree underscore sum. Asterisk calls post order, root, to start the traversal. Asterisk returns the split underscore count and the, potentially, modified root node of the tree. 3 example usage asterisk. Asterisk creates a sample tree with nodes and their values. Asterisk calls tree underscore vertex underscore splitting underscore greedy to perform the splitting. Asterisk prints the number of splits and the final values of the nodes in the modified tree. How the greedy approach works in the code. The post order function recursively traverses the tree in a bottom-up manner. For each node, it calculates the sum of the values in its subtree. If this sum is negative, it means the subtree is unprofitable and needs to be adjusted. The greedy choice is to split the current node, reduce the value of node. Improvements and alternatives. 1. Dynamic programming asterisk for optimal solutions, dynamic programming techniques can be employed. The key idea is to build a table storing the minimum number of splits required for various subtrees and value allocations. 2. More sophisticated heuristics asterisk instead of a purely greedy approach, you could consider heuristics that look ahead a few steps to see if splitting now will lead to more splits later. This might involve evaluating the potential impact of a split on the values of neighboring nodes. 3. Linear programming asterisk the tree vertex splitting problem can be formulated as an integer linear program, ILP. While ILP solvers can be computationally expensive for large trees, they can guarantee an optimal solution. Summary. The tree vertex splitting problem is a fascinating problem with applications in various domains. The greedy approach provides a relatively simple and efficient way to obtain a solution, but it's important to remember that it's not guaranteed to be optimal. More sophisticated techniques, such as dynamic programming or linear programming, can be used to find optimal solutions, but at the cost of increased computational complexity. Understanding the trade-offs between efficiency and optimality is crucial when choosing an algorithm for this problem.